Hi, everyone. Today we're going to talk about sections 6.3 and 6.4, continuing with propositional logic and truth table analysis of propositions. But I want to go over the exercises that were assigned for 6.1 and 6.2 and just kind of give you the correct answers for that. So the first ones we have, and I have them written on the board behind me as well. See if I can move it so you can see the last one. Well, I'll move it when I get to it. So 6.1 is translate each of the following statements into symbolic form. And as I've said before, the advantage of propositional logic is that you can more easily translate normal sentences into propositional form. Like, let's take the first one. Cartier does not make cheap watches. So how would you put that into a categorical form? You could do it, but it would take some finagling to get it done. Whereas in propositional form, as you see behind me, the first one is just not C. For number 3, either Stanford or Tulane has an architecture school. And so that's S for Stanford, the wedge for the or T. So that's for 3. 5, if Chanel has a rosewood fragrance, then so does Lanvin. This is an implication. So C for Chanel and L for Lanvin, though C, then L. So 5. Number 7, Maureen Dowd writes incisive editorials if and only if Paul Krugman does. So the if and only if is a biconditional, and so that's the 3 lines. So M for Maureen Dowd and P for Paul Krugman. So M, triple line, P. 9, Armani will launch a leather collection given that Gucci rejects skinny models. So given that basically is like given that if Gucci rejects skinny models, then Armani will launch will launch a leather collection. So that becomes an if then. So that's G then A. Okay. Number 11, Bill Gates does not support malaria research unless Warren Buffett does. So the unless makes it a wedge. So Bill Gates does not support malaria research, so not be wedge W. Okay. 13, Mariah Carey sings pop songs, and either Elton John sings rock or Diana Krall sings jazz. So you have Mariah Carey sings pop songs, so M for Mariah Carey. And then either Elton John sings rock or Diana Krall sings jazz. So either E for Elton John and D for Diana Krall. So as you see, M dot and then parentheses, E wedge D. 15, not both Jaguar and Porsche make motorcycles. Not and then parentheses, J for Jaguar and P for Porsche. Now we move up to 17. 17, either Apple or Samsung make smartphones. A wedge S, as simple as that. 19, neither Ferrari nor Maserati make economy cars. There's 2 ways to say this, and we'll learn about this later when we do De Morgan's theorem. The one is not, and then you're denying either Ferrari or Maserati make economy cars, so F or M. You deny that, so the negation sign over the F or M, or not F and not M. Those are 2 ways of saying the same thing. Number 21, if Bill O'Reilly spins the news, then if Chris Matthews fights back, then Rachel Maddow tells it straight. So that's if Bill O'Reilly spins the news, so B, horseshoe for the conditional. Then, and so we have another conditional, if Chris Matthews fights back, then Rachel Maddow tells it straight. Then C, implication R. Okay. 23, Tommy Hilfiger celebrates casual if and only if, so we have biconditional again, the triple wedge, if and only if neither Ralph Lauren nor Calvin Klein offer street chic. So the tilde negation sign and the parentheses R or C. And the last one for this was either Rado does not make a sapphire watch, or if Movado makes one, then so does Pulsar. So it's not R for Rado does not make sapphire, or and then it's M for Movado makes one, then implication Pulsar does. So M implication P. So we basically got that set. That was that for those. Again, if anyone has any questions about that, post it to the discussion forum that I've put up. The next sections that I assigned was 1 through 10. Here, determine whether the following are not well-formed formulas. So this was on the bottom of page 340 over to 341. So I'll just give you the answers to these. Number 1 is a well-formed formula. Number 2 is not, because you have the implication before the G in there, so it makes it not a well-formed formula. Number 3 is not. You can't have the negation sign between two variables like they have there. Number 4 is. Number 5 is not. You have to have the parentheses around the E or T, because otherwise it's not clear. Number 6 is well-formed. Number 7 is not. You can't have the dot before that last H. Number 8 is not. You can't have the first M without some sort of symbol function going on between the M and then the parentheses. 9 is well-formed, and 10 is not. You can't have the dot and the negation sign, both in that way. It would have to be in parentheses. So that's how that works. And then for 6.2, I did section 1, 1 through 10. So this is identify the main operator in the following propositions. So that's what's the one that connects the two statements together. And so 1, it's the dot. Everything left of the dot is one statement, and everything to the right of the dot is another statement. Number 2, it's the horseshoe. So everything to the left, the G dot negative P is one, and everything to the right is another. Number 3, it's the tilde, the negation sign outside the brackets. Number 4, it's the triple bar is the main operator. Number 5, it's the wedge after the M dot B. It's the wedge is the main operator. Number 6, it's the negation sign, the tilde, because you'll notice everything after that is in brackets, so it's the final thing that you do. This is kind of like what you might have had in other classes, the order of operations. So it's the last thing that you do when you do the truth tables. So that's why it's important to know what the main operator is, because that's the last truth table calculation that you figure out. Number 7, it's the horseshoe. And number 8, it's the triple bar. Number 9, it's the dot after the E. And you notice what's after the dot is all in brackets, so that's one big compound statement. So you would all do the truth tables of that first before you then did the E dot and whatever the truth value there was to get the final truth value. And number 10, it's the wedge is the main operator there. Again, I would be stopping just to make sure anyone doesn't have any questions, but at least now you have a video. You can always pause it and go back, get the answers again if you didn't hear it the first time. So section 3, 1 through 25, odd. So what I'm gonna, I'll give you the odd 1 through 25 odd here. So basically what you're to do is to determine the truth values of the following statements. A, B, and C are true. X, Y, and Z are always false. So you basically just do the truth functions like we looked at before, like we did in class on Thursday, the Thursday before I left town, and determine the final truth value. So for 1, if you did A is true and X is false, the true dot false is false, right? So that's how that works. And I will have done that in class. Actually, I will have done 3 too. The X wedge not y, would be true, because x is false, but y is false and made true. If one of them is true, the whole thing is true. So 3 is true. So I'll give you the rest of the answers, the odds. 5 is true. 7 is false. 9 is true. 11 is true. 13 is true. 15 is false. 17 is true. 19 is true. 21 is false. 23 is true. And 25 is true. As you can see in that last one, 25, it's quite a doozy. It's a big, big one. But if you look at it, again, that's why the main operator was the key. The main operator is the horseshoe after the Z implies C. And so you get the truth value for, so Z is false and C is true. So that's true. So on the left of that horseshoe is true. And if you have to work out all the truth values of all the others, and it ultimately works out to be true. So it ends up being a true compound statement, but a complicated one. So it does take, but as you start doing, by the time you got to 25, hopefully it was somewhat easy and somewhat mechanical for you at that point. And that was it for the exercises that I assigned last time. So now what we're going to start doing is we're going to start looking at truth tables for propositions. We just looked at truth tables for functions, but now we're going to actually begin to use truth tables to analyze arguments. So I'm going to turn to 6.3, and we're going to look at, and I'm also going to be looking at the book, so you're going to want to have the book out too, because some of these are long. I'm not going to write it all out on the board, but I am going to write one out on the board, which is all on page 355. It kind of shows you how to go about determining the truth value. This pen is not doing well. Let's see if this one's doing better. Okay. Okay. So you'll notice on the page before, if you have a single proposition, A, you have basically two options. It's either true or false. Right, so there's two possible truth values. But if you have two, which is what we have here, you have 4. And so let me show you. And the way to go about doing this is you have true, true, false, false, true, false, true, false. Okay? That covers all the options, right? Either A is true and B is true, or A is true, B is false, or A is false, B is true, or they're both false. That covers all the options. So what we're going to do is we take with two propositions, we can go through all the options and determine what all the truth values are. And this will give us a way of analyzing propositions, whether they're tautologies, self-contradictory. We can also do it to analyze whether arguments are valid or not. So it becomes a very handy way of looking at arguments. So if you'll look on page 355 of your text, they fill in the left here, I guess that's left, as I have just done on the board. And then they begin filling in the truth table. So they do B within here first. So what happens with B, we have B here is true, but you see the negation sign. The negation sign makes it false. So that's why I've written it under and that's why they have written it under the negation sign as well. And so the false becomes true, the true becomes false becomes true. And the A stays the same, right? The A stays the same, but now we want to determine the truth value of the wedge. So that the only time that is false is when they're both false. Any other time it's true. So true or false is true. True or true is true. False or false is false. False or true is true. Okay, so that's how they got the true, true, false, true on the bottom there of page 355. And now it's a matter of doing the implication. So the implication, we now have B is, let's just put in the B values here, right? We know that B is true, false, true, false. So the only time an implication is false is when it's a true antecedent and a false consequent. So we have true, true is true, true, false is false, false, true is true, true, false is false. Which is the answer that they gave at the top left of page 356. And then I'm not going to write this one up on the board. It's basically a longer version of the same thing. They give the C dot negative D and implication E. But now you have 3 propositions. And with 3 propositions, it's going to be 8 lines. And so the way you write it there is you divide the 8 in half. And so for the first of the 3, C, you go true, 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 true to get the 4. And then false, 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 false to get the other 4. Then for the second proposition, you divide that in half. So it's 2 trues, true, true, false, false, true, true, false, false. And then the third, then you alternate, true, false, true, false. And that will cover all the options. And then you go through, just like I did with the example there behind me, and fill it all in, going back over the truth functions and just filling in what is true, what is false, and you end up with the truth values that they show on 357. So it's all fairly straightforward. And so what can this do for us? How can this help us? So this brings me to 358 in the textbook. So under classifying statements, there are 3 types of statements. There are tautologous, self-contradictory, and contingent. So at the top of 359, you'll notice they have this G implies H and G, and all of that implies H. If you do the truth table analysis of that statement, you end up with all true. That is a tautologous statement, meaning it's true in every circumstance. So that's why a tautology would be like all unmarried men are bachelors. It's just another way that's always true. It's never, there can't be a circumstance where it's false. The statement next to it, G or H, and then triple bar, not G and not H, you do the truth table analysis of that, and you find out that they are all false. So that becomes self-contradictory. So that's one of those things where it's always false. There's never a circumstance where it's true. So what's the other option? Sometimes there's a true and a false. There's a mixture of both. So if there's a mixture of both, then that's a contingent statement. And those are the statements that are meaningful, right? It tells us something, that under certain circumstances it's true, but not always. If it's always true regardless, then it becomes tautologous. If it's always false regardless, then it's a self-contradictory. So there will be some exercises where you go through the statement analysis and you determine what kind of statement it is. And some of the answers will be tautologous, self-contradictory, or contingent. So that's looking at a single statement, right? You're just looking at what one statement itself is saying. But now you can compare more than one statement. So statements will be separate statements here. And if you go through, and there's 4 options here. This is listed at the bottom of 359. The 4 options are either logically equivalent, where you have the same truth value on each line, meaning it's basically they're saying the same thing. The second is that they're contradictory, that those 2 statements are always saying the exact opposite of each other. The third is that it is consistent. There is at least one line in which truth values are both true. So to be consistent means that at least they're saying the same thing both times, and it's true. Inconsistent means that they aren't saying the same thing. So there is no line in which the truth values are both true. So if you accuse someone of being inconsistent, you would say, just a famous example in political debates, given that we are heavily in politics debating in election season, Abraham Lincoln, when he was running for president in 1860, was accused of being inconsistent, that in south of Illinois, he ran, actually this was when he was running for Senate, when he was running for Senate in the south of Illinois, he was accused of giving pro-slavery speeches, that slavery is good. And then in North Illinois, he would have said slavery is bad. So those are inconsistent statements. You can't say one and it be true, and then say the other and the opposite and it be true too, right? They can't both be true at the same time. So that was what he was accused of inconsistency, therefore, that there wasn't a line where they were saying the same thing in both contexts. He claimed that they took what he said out of context, a very political kind of thing, and argued that he wasn't being inconsistent. So those are the kinds of statements. And so over on the next page, they give us some examples. So on the left, there we have the K implies L is one statement. And then the not L implies not K is the other statement. Again, those are 2 propositions, so there's going to be 4 lines to it. And if you work out the truth table analysis, you'll see that the first line of the one is true, same for the other. Second line is false, same for the other. Third line is true, same for the other. Fourth line is true, same for the other. Same truth value, both lines. Doesn't matter whether they're true or false, as long as they're the same on each line, then it's logically equivalent. Now, if you were just looking at the statement by itself, you would say it's a consistent statement, right? Because there's a mixture of true and false. So we have 2 contingent statements that compared are logically equivalent. Okay, that clear? So a contingent statement is not a tautology or not a self-contradiction, but something that has both a true and a false value as an option. And that's what you have in the 2 statements there. But not, and then when you do the truth table analysis, they have exact same truth values, so they become logically equivalent. So the next one, if you go do the truth table analysis, you see that the opposite truth values are at each line. Line 1 is true in one, false in the other, false in one, true in the other, true in one, false in the other, true in one, false in the other. So these become contradictory. So now we have the 2 other options that are slightly different. We have consistent. So you'll notice that in the first line of these 2 propositions, K or L, and then the second one, K dot L, we have truth values on the first line. It's true in the first line, K wedge L, and it's true in the second line of K dot L. But they have opposite truth values in the second 2 lines, and they're both false in the third. So as long as there's a line where they are both true, then it's consistent. And if you look at the last one, the K triple bar L, and then the K dot not L, you'll notice that there is no line where they are both true. So therefore, that's an inconsistent statement. So that brings us through 6.3. So the exercises, again, are section 1, you're to use truth tables to determine what kinds of statements these are. Are they tautologous, self-contradictory, or contingent? In section 2, you're to do 1 through 15 odd, and basically here you're comparing statements. So just the stuff that we did, used, again, truth tables to determine that. So I'll go over the answers in the next video. I'll go over the answers to those. Okay. Now it's time to look at truth tables for arguments. I'll start like I did last time around with one on the board. Okay, so this is going to be actually kind of a helpful analysis because for those who remember, this J implies E, not J and not E. I've already discussed this as one of the standard forms of argument that is a fallacy. It's called denying the antecedent. So you can come up with a scenario where the premises are true and the conclusion is false. So anytime you can come up with a scenario where the premises are true and the conclusion is false, you know it's not a valid argument. So a valid argument means if the premises are true, then it's necessarily the case, logically necessary, that the conclusion also be true. So what we're going to do then is do a truth table analysis of this and show that. So the way to do that Okay. All right, so if you'll notice, the J implies E is the first premise of the argument. The not J is the second premise of the argument. And then we have these two forward slashes is what goes between the premises and the conclusion. It's clearer in the book. This pen wasn't working that well there. So now we just do the truth table analysis of that. And so we begin with the first term listed, and that's J. There's only two terms, so we know there's only four options. So true, true, false, false, true, false, true, false. And now we keep the same all the way through, so that would be true, true, false, false, and E, true, false, true, false. Okay. So now let's go through the rest of the analysis. So very simple. It's all should be pretty easy, hopefully, for you by this point. So in these implications, it's true in all cases unless it's true implies false. So that's true, false, true, true. So that's this one. Okay. Now here we have the J, but the negation sign flips the truth value. So that makes this one false, false, true, true. As you do your homework, especially in some of the longer ones, I don't know, it might be helpful if you have graph paper. It might, whatever's going to help you to make it straight so you don't kind of get the lines messed up. Don't worry, on the test, I'm not going to give you one with 16 lines that you're going to have to do. So take the E, flip that truth value around, and that makes that false, true, false, true. And if you look at this argument, you'll say, look at the first line, true, false, false. Okay, no problem there. False, false, true, no problem there. True, true, false. Aha. So now we have shown by that truth table analysis that we have a line where the premises are true and the conclusion is false. And so we know by this truth table analysis that this is a invalid argument. And we could take a valid argument and we can show that there is no scenario where, so if we had switched it around and did J implies E, J, E, we would have these. We wouldn't have had these truth values, and we wouldn't have had these truth values. And you'll see we don't have true, 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 false, true, false, true, false, true, true, false, false. We don't have a line where it's two truth values and a false conclusion. So there's no scenario where we can have true propositions and a false conclusion. So that's valid. And that's, again, that's modus ponens, which we know is a valid logical form. The one that I had done before is denying the antecedent, which we know is a invalid logical form. And so we've just now used truth tables to prove that the one is valid and the other is invalid. So this gives you an idea of how you can use truth tables to argue for analyzing arguments. So the last one I want to look at is actually, I think that's good. I think we're done. I was going to look at the argument. Well, I'll read what he says. Very bottom of 366. And then we'll be done for today. It says, truth tables provide a convenient illustration of the fact that any argument having inconsistent premises is valid regardless of what its conclusion may be, and any argument having tautologous conclusion is valid regardless of what its premises may be. So example he gives is the sky is not blue. I mean, the sky is blue, the sky is not blue, therefore Paris is the capital of France. And if you look at that, you do the truth table analysis of it, as I do at the top. You get true, false, true, false. So you end up with, you don't end up with two true premises and a false conclusion. So you still end up with a valid argument, even though it has a contradiction in it. Which is, again, one of the reasons why you don't want to allow for contradictions in an argument, because then you can prove anything, right? And we'll see that later on. So if I have S, not S, and I want P to be, I don't know, moon is made of green cheese, then you can make that a valid argument. And there's other ways to do it, which we'll see later on, that makes contradictions even more problematic. So contradictions in an argument are not part of validity here. When we're thinking of valid form, we're thinking of true premises and true conclusion. So that's it, I think, for that. So what we're going to do then for the exercises, 6.4, you have to actually I'm only doing section 2, 1 through 10. Use truth table analysis to determine whether the following arguments are valid or invalid. So remember, they are invalid if there's two lines of the premises that are true and a line in the conclusion that is false. So in the next video, I'll go over all the exercises, both for 6.3 and 6.4, and then we'll also go on and talk about 6.5 and 6.6. So that's it for today. Hope you have a good rest of your day or evening, whatever time it happens to be for you. I'll see you all in the next video.